Good morning, we are at Technische Universiteit Eindhoven. My name is Lou Feijs and today's topic is the mathematics of fashion. By inspiration I show you this short video clip which gives you a flavor of the things to come. Fashion is a big area, so today we're going to zoom in on one specific motif, a pattern called pied de poule. I will explain what is pied de poule, its role in fashion, the mathematics of pied de poule, and translate that into an example in the processing language so you can generate your own patterns. We will also show an example of an innovation done here in Eindhoven. These are the resources. So the slides, the processing program, and a link to an article, Geometry and Computation of Pied de Poule, which has been published at Bridges. What is pied de poule? Here we see that actually different nations, different languages have different names for it. In France they call it pied de poule, which means the foot of a chicken. In Dutch and in Germany they call it hanenvoet or hanentritt, which means like the footprint of a rooster. The English-speaking languages call it houndstooth, and in China it's translated like the thousandth bird pattern. It looks like this. It arises in weaving by the interplay of the warp yarns and the weft yarns. It looks like this, and it's created on a machine which is called a loom. The loom is where you have two sets of yarns, the warp and the weft. One goes in the longitudinal direction, the other crosses through. There is a shed, which means there is a little bit of space between the warp yarns, and then there is a shuttle which goes through, shooting weft threads. The shafts, they control the going up and down of the warp yarns, so you can have interesting patterns of going over and under, which is called the binding. And there are several types of binding, like the plain weave or the twill weave, which I will explain later today. How is it used? Actually, it has been in use already for many centuries. Here you see a reconstruction of a found 300 years BC in Scandinavia, where they already had this houndstooth pattern. Here you see an advertisement from the 19th century where it was already fashionable for sewing and garment construction in the Netherlands, as is witnessed here. And in France it has been introduced, for example, by Dior, as you can see here. In the United Kingdom it's attributed to the Prince of Wales, who used to be very fashionable and who introduced the same pattern in England. It's a very common thing for women's fashion. Here you see the last Karl Lagerfeld show for Chanel, very big pied de poule prints. Here you see an even larger version. Here you see Her Royal Highness Queen Maxima together with the Queen of Belgium. It's very showy. If you do it in men's fashion, it better be rather subtle. So this is Oqui and Wezor. He used to be the head of the Venice Biennale, and you see it's much more subtle. The same can be seen in my own garments. For example, this jacket. It's a special fine-grained type of pied de poule. We call it puppy tooth. And later I will explain that actually there is a family of pied-de-pools, and this is the number 1 in that family. It's very subtle. You can also see a slightly larger grid in my tie, and it's subtle in the sense that it's a shiny type of black woven with a non-shiny type of black. So it's a full-blown pied-de-pool, but from a distance you don't see it. You have to look carefully to see the subtle effect. The mathematics of pied-de-pool, there are 2 aspects of it. One is computational, so if you want to generate such patterns, then we need to work with modulo arithmetic. We will see formulas like I modulo 8 less than 4, and similar coding of the binding of the weaving. At the same time, tessellation theory is applicable, like the H type, and it's interesting to consider the contour of the basic tile. It's important to understand that pied-de-pool arises by weaving, and there are several types of weaving, like the plain binding or the satin binding, where you have long jumps, long floats as we call it. But you also have these bindings which are called twill bindings, where rather than 1 over 1 under, if you consider the warp, you have things like 2 over and then 2 under, and repeating that. That makes a difference, particularly raincoats, but also pied-de-pool patterns, they're done with twill binding. Here you see how it happens. So the warp, these are the vertical yarns, they are organized in a white and black pattern, 4 white, 4 black, 4 white, 4 black, and so on. And the same is the weft, which is shot through the warp, 4 white, 4 black, 4 white, 4 black. And then if you combine this with a twill binding, 2 over, 2 under, this pattern will emerge. So it's not printed, it appears from the weaving in a kind of natural way. If you zoom out, you recognize the very characteristic pattern here. Notice that it's a tessellation, so you can recognize the black tiles, you can recognize the white tiles, and actually they are the same. Of course, you can ask what is precisely the basic tile, because you would consider some freedom in where to make the cuts. After all, the black tiles, they touch each other. But if you just take the shortest cut, this is the unique basic tile of pied-de-pool. Actually, the pied-de-pool is a family. You see that here. So these are the types n equals 2, 3, 4, 5. And the last one actually is a kind of limit case. You don't see the staircases anymore. If you take the family number n and you take it to infinity, you get a limit, which is this symmetric tile. Note that the other tiles are not precisely symmetric, they're almost symmetric. The pied-de-pool is a member of a larger family, so if you work with these alternating black and whites in the warp and in the weft, you either get these block patterns or you get the pied-de-pools, and then for the n equals 1 member of the family, they coincide. So you can have a look at it and say, yeah, I see here what is the basic tile, it's this little windmill. But you can also say, no, I have another view on it. It's the basic block of the poppy tooth, which is the simplest of the pied-de-pool family. So there is kind of interesting ambiguity there. Now I will continue this at the light board. First we address the warp, which is the set of yarns which here I draw vertically. There are many of them parallel. I just draw a few of them in this direction. And what we want is that they have different colors, like 4 whites, 4 blacks. So this one white, 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 and then 4 blacks, black, 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 and then 4 whites again. So that's what we want, 4 of them, and then repeat. How can we develop a formula for that. We will do that using an operator called the modulo operator. I will explain the modulo operator by a division. So consider a traditional long division like 133 divided by 8. That goes 1, 8, 5 left over. We add the 3, now we can try 6 times, 48, left over 5, and now we are stuck. This 5 is the remainder, and in mathematics we would write like 133 equals 5 when calculating modulo 8. In programming, the notation is slightly different. If you have a program like x becomes 130 through modulo 8, then the outcome is the same as doing x becomes 5. So this is the notation we will be using here. We can use that for the warp problem to get this 4 white, 4 black. If we assign integers to the warp yarns, like I being 1, let's start at 0, that's better, then 2, 3, 4, 5, 6, 7, 8, 9, 10, goes on like that. Now we can, for each of those integers, calculate I modulo 8. And then we get 0, 1, 2, 3, 4, 5, 6, 7. But here it starts again at 0. 0, 1, 2, 3, 4, 5, 6, 7. So that embodies the idea that after 4 whites and 4 blacks, so after 8 warps, it continues again. So the test to get the first 4 of these is the test whether I modulo 8 is less than 4. It's the case here, so here it's true, here it's true, here it's true, here it's true, but now 4 is not less than 4, so here it's false, 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 and then it moves back to true, true, etc. So if we assign true to white and false to black, then we have the intended pattern. We can do the same for the weft. So you know the weft are the yarns which go here, like perhaps they go under and then over and then under and then over, and the other one, well, depends on the binding, but this is called the weft. And for the weft we can do something similar. We work with numbers j equals 0, 1, 2, 3, etc. And we get a similar formula, the formula being j modulo 8 less than 4. The big plan from this is that we're going to have this pattern with 4 whites, 4 blacks, 4 whites again. We do the same in the weft, say like this, 4 blacks, you don't see them. So here in this area, it's clear that everything is white. In this area, it's clear that everything is black. The interesting thing happens, of course, in this area and this area. So the next task is to develop a formula which describes the binding, how the yarns go over and under each other. That's the next task. Now we have formulas for the basic material, but we don't have a formula for the weaving itself yet. And to start simple, first I will talk about the plain binding. which is the simplest form of weaving. So I cannot draw it at once, so this is, I make dots where we will have the weft, and then later I will see whether the weft is over or under. These are the locations of the weft. Now let's try some warp. Say the first warp goes over, then it goes under, the next goes over, the next goes under. It goes like that. And then the other one, it shifts by one. So rather than going over here, it goes over here. Under, over, under. Of course, here it's also under. And then shift by one again. So here you see the general pattern. Successive warp yarns, looking at the given weft, they go over, they go under, and they repeat after two. So that's the plain binding. This is like my shirt would be poplin. It's the most used binding, but twill bindings are more sophisticated. In Dutch we call them keperbinding. And that's the idea of going two over, two under. So first let me try and draw the location of a few of the wefts. In the loom it goes differently. Then there are shots, and there are the shafts which control the warp yarns, which are grouped. If you have a jacquard loom, you can do it for every crossing individually. So here you have some candidate wefts. Now the warp is more complicated, so it goes over, under, so two under, and now two over, and then two under again, and the next one shifts. So now we start with two over, under, two over. Let's do this one as well. It goes down, so the two over is here, under. So this must be an under as well. Here we would even have two under, two over, two under. So you see the general pattern. The general pattern is two over, two under, and then repeat after four. The trick is that although it's two over and two under, the shift between two successive warp yarns is just one. So that's what makes it interesting. Otherwise you get what they call a basket weave, shift over one. Now how would we do that in a formula? If we look at a fixed J, say J equals 0, and then we see what successive warps are doing here, it's quite easy. So here it goes, the question is whether it goes over or not, warp over, and yes, it goes over. Here it goes over, here it does not, here it does not, here it goes over, here it goes over, here it does not, here it does not. So actually this would be easy to capture in the formula. We know that by now. That would be like I modulo 4 less than 2. But now we want for the next weft, it should be different again, which means that we are going to modify this formula and we turn it into this, namely we subtract I and j and then do the same thing. That will have the effect that each pattern shifts by 1 if we increase the j. There is one additional trick we do here. If you have this modulo operator, it's well defined and well explained for positive numbers. If you work with negative numbers, then the mathematics and the programming traditions tend to be different. I avoid all of that mess. So with the I prefer to start counting at I being, say, 1000, and the next being 1001. For the modulo calculations, that doesn't make a lot of difference, because 1000 can also be divided by 4, but it makes sure that if I do I minus j, I will not easily run into negative numbers, at least when I'm making the patterns not too large. So this is the basic idea, and now we can compose all of this into a single formula. It's kind of if then else. So the Aij, so I consider this to be a kind of matrix with all these Boolean values, and then the general entry is called Aij. That's depending on the binding, so you could say it like this: if I minus j modulo 4 less than 2, then the warp is on top, so we will see that, C warp. Else see the weft. And what does it mean to see the warp? Well, seeing the warp means that it's going to be white. We had a formula for that. So that's the formula we can plug in here. I modulo 8 less than 4. And for the weft, we also have a formula, j modulo 8 less than 4. So if you put this together, we have a single formula which describes the pied de Poule. Now we have this theory and this calculation, this modulo at our disposition. I will show you an example in processing. So the example will generate a pied de Poule of the type n equals 2, but with small modifications we will also have the other pied de Poules and other interesting twill patterns. Here you see the program. So we have counters, I running horizontally, counting columns, j running vertically, counting rows. We initialize at I being 1000, so that avoids taking the modulo of negative numbers. And then, of course, 2 nested for loops, and the key formula, the central formula which codes the essence of the pattern, is in the center. Aij is, and then it's an if then else, so the condition is I minus j modulo 4 less than 2, question mark, so that controls the binding. And then in the if clause it says I modulo 8 less than 4, so that governs the white and black pattern of the warp. And the else clause is j modulo 8 less than 4, which codes the same block pattern in the weft. And if the outcome of this is true, then we make a white block. If the outcome is false, then we make a black block. That's all. Let me show you some results. Here you see for n equals 2 what comes out. And we can run the same for different values of n. So rather than 4 modulo 2, we can do like 6 modulo 3 or things like that. So here you see in the code which is on GitHub, you can get this formula, but also the other ones which are in comment now. And then you get the other version. So this is the puppy tooth. This one we have seen already. This is the next version. This is the next version in the family. it goes on like that until there is this symmetrical limit case, but you need another program for that. In the code there are also different formulas for checkerboards and for grids. Here you see the checkerboards, they're easy of course. Here you see the more subtle type of grids, which you in real life see, for example, in the trousers of chefs. There are more, like the herringbone patterns and broken twill. Here you see those. You would typically see them in big overcoats. This one is it has a slightly more complicated formulae. It's called goose eye, and well, here you see an example of a fashionable shoe, which shows that these things really play a role in fashion. Recap and reflection. So the Pied de Poule is an industrial and cultural phenomenon. It's alive in today's haute couture and in commercial fashion. The geometry and computation are by now well understood, and here in Eindhoven, TUI and a company called ByWire.net, we refine and innovate the pattern. And for that we use fractals, cellular automata, topology and emerging technologies. We brought one example. It's here on the mannequin. It's a fractal version of the Pied de Poule, which has been made using a laser cutter. Here we see this example where the Pied de Poule pattern has been turned into a fractal. It means if you zoom in, you get another Pied de Poule. If you zoom in, you get another Pied de Poule again. It has been realized in this garment, which has been made by laser engraving, and it has been done with TUI in cooperation with the company called ByWire.net. That's it for today. Next week, we're going to do more mathematics of fashion. Thank you for your attention.